Hello physics students. Welcome to our next topic, optics. Now you may be thinking that the view of the camera looks a little different today, and that's because I have all the lights on in my classroom and the shades pulled down. So it's pretty dark in here. In fact, it's darker than the view you're seeing on the camera because cameras compensate for dark conditions and try and brighten things up a little bit. So it's pretty dark in here. And that's on purpose because a lot of optics is actually studied in dark rooms because what we're doing is we're studying the behavior of light. And so we try and isolate all the light, the ambient light, get it away so we can analyze the light in the experiment without any interruptions. So it's a great setting for experimentations. It's a lot of fun optics experiments often. In fact, some of them are even done by candlelight, which is actually a great way to study physics. And no, I'm not making a joke. Most of the physics that we studied this year was done or discovered more than 100 years ago, before there was electricity, before there were electric lights. In other words, by candlelight. So anyway, I'm getting a little off topic because I'm a little excited for our demonstrations today. So optics, as I said, is the study of light. And we already studied light a little bit in the waves unit, the last topic. And basically we learned that light was a wave which is a vibration of electric and magnetic fields. So if I take this meter stick like this, representing the direction the wave is traveling, the light, the electric fields are vibrating perpendicular to that, maybe, let's see, how can I hold this? Up and down like this. So like this kind of oscillation. There's also magnetic fields that are vibrating perpendicular to the electric fields. So we've got electric fields vibrating up and down like this, side to side magnetic field vibrations, and those vibrations are traveling to the right of your screen like this. And so, because the vibrations are perpendicular to the direction of the wave, light is a transverse wave. So what are some other things that we learned in the waves topic about light? One, it can go through a vacuum. This is why we can see the sun coming from outer space. The light comes and reaches us and brightens our day. But we can't hear the sun because the sun is actually very loud. If you were on the sun, lots of violent activity. But the sound cannot travel through vacuum, light can. Light can obviously travel through air also because you could turn a light bulb on and the light goes through the air. So light can go through other materials, but not necessarily all materials. It can't go through a block of wood, for example. The other thing is light travels extremely fast. 3 times 10 to the 8th in a vacuum, which is 300 million meters per second. In other words, as I mentioned in the waves topic, if you could wrap it around the Earth, it would go around 8 times in 1 second, extremely fast. So it travels through air pretty much that same speed. So when you turn lights on, it moves pretty much, in our view, instantaneously from one point to another because we can't perceive those small differences it takes the light to travel. Other things about light. Light can do what all waves can do. Like it can reflect through the process of reflection. So reflect, reflection. It can also, we learned, diffract through diffraction. We learned both those things in the last topic. And it can also do a third thing like all waves, which we haven't learned about yet, but we're going to learn in this topic. It can refract through refraction. So all those terms sound different. Let me just summarize again. Reflect, reflection. That's 1. Diffract, diffraction, that's 2. And 3, refract, refraction. So let's begin by just looking at light in particular. What I want to start with is the concept of diffraction. Remember, diffraction is when a wave passes through an opening and spreads out and fills the chamber that it's going in through. But here's the thing. It only does that if the opening it's going through is small compared to the wavelength. So when I talk and my sound goes through a doorway, the sound waves are so big that the doorway seems small to the sound. But to light, the wavelength is tiny, tiny, tiny. It's less than a millionth of a meter, even for the longest light wave of red light, less than a millionth of a meter. So to a light, the doorway is humongous. In fact, if I look at this little opening here, little issue with focus here. Okay, see that opening right there? That slit in this white piece of plastic? You would not say that's a big opening because it's probably about a millimeter across sideways. But to a light wave, that is an enormous opening. To red light, thousands of wavelengths can fit across this gap here. So an analogy would be if you walk through a doorway that was more than a mile wide, that would be the experience of light passing through this tiny opening. It's like a doorway a mile wide to the light beams that are so small, the light waves, I should say. And so that then means that light, because it's so small, it doesn't tend to diffract as much. I see my focus is now messed up because of low light conditions. So, all right, I guess we don't need too much focus, so I'll be blurry for a while. So if I take this light and I turn this bulb on, then basically it's sending light out in all directions. And we could just verify that by me putting my hand here. You see how it's illuminated. So that means the light is going toward, I guess that would be your left. But it's also going toward your right because my hand up here is illuminating, and up. So this is radiating the light in all dimensions. But if I take this little device and I put it in this box, so here's another identical light in here, and I put this little plastic sheet over here so that the light will then have to pass through that little, to us a little doorway, to the light a huge doorway. It will not diffract. As we can see, the light passes and does not spread out after it goes through that opening. Again, it's because the wavelength is so tiny compared to that opening, so it's kind of like a shadow in reverse what we're looking at. If we had a light source going out in all directions and you put something in the way, there'd be like a dark line of shadow. This is like a bright line, a shadow in reverse where the light doesn't spread out around to the paper here. So light, very nice. You can make a beam of it pretty easily because of its short wavelength when you let it go through an opening. In fact, you can create a beam with a little laser like this. And I'll turn this on, and you could see this light up, but you can't see the beam. And the reason why is because the light can pass through the air without interacting with it, so it looks invisible, but the light really is flying across the screen right now. I could show that by moving this paper along and showing you that it does trace out a path across the screen. But there's a better way, which I don't have to show you, but I'm having fun with demonstrations and I like playing with all my little optics toys. So I'm going to show you another way we could see this light, how because it doesn't diffract, through the opening of this end of this laser, it makes a nice beam of light. So let's take a look. What I've created is a little smoke chamber. I did that by taking a board and putting it over a desk with a few inch gap and lighting 4 sticks of incense underneath the board. What that does is it creates particles that allow the laser light to scatter. Again, when the laser light goes through pure air, it doesn't scatter. We can't see the beam. But here with the smoke, we could see a nice bright image whenever the laser light hits the smoke beam. Again, what we're showing here is that light makes a nice collimated beam because it doesn't readily diffract because of its short wavelength. But I can also show you a few other colors here. Here I have a green laser. That looks very pretty. And even a blue or purple laser, which doesn't show up that well on the smoke particles. Really beautiful to watch these smoke particles dance in the laser light. What I'm going to do now is try and get all 3 to light so we get a nice demonstration of laser light. All right, there it is. All right, so let's go to the board and summarize what we learned about these collimated beams of light. That was fun. But let's now summarize. So I've got my laser here producing this beam of light as shown by this red arrow. And that beam of light in optics we call a light ray or just a ray. And it's just this imaginary thing that helps us to analyze what light is doing in a whole bunch of circumstances. But what a light ray is it's this arrow that's perpendicular to the actual wave fronts because the light is coming like this, crests and troughs, and we imagine this line of light that we call the light ray. Now, I drew this out of scale because, again, light is so small of a wavelength that I'd be drawing a zillion lines like this and then it'd be just solid chalk. So I'm drawing the wavelength too big for light. But this is a schematic, gives us an idea of how to draw a light ray, draw a line, an arrow perpendicular to all the crests of the waves, and that's the light ray. So let me create a pause to give you a chance to copy these notes down. All right, now, this is going to help us to understand what light does when it reflects. Because we learned what reflection is when we did this, we studied this slinky like this spring, but that was simpler because that wave was confined to the spring, which was like a one-dimensional reflection. But light can careen off into all three dimensions. So let's take a look. And first of all, the thing we're about to learn about the pattern of what light does when it reflects is called the law of reflection. And so if you take a light, like a laser beam like this, and you target it at a smooth surface, the smooth surface could be obviously a mirror, which is metal. I don't know if you know that, but metal that's been polished very smooth. You could take a rough piece of metal and keep polishing it down, and eventually it'll be a mirror, it'll be reflective. But it could also be a sheet of glass or a water surface that's very smooth. When the wind's not blowing, you could get reflections off of that. It has to be just a smooth surface. The light ray comes in, so we call this the incident ray. And then it reflects, and we call that the reflected ray. The light reflects in a pattern like this, that whatever angle it comes in, it goes out at the same angle. But here's the thing. A lot of students make this mistake that they measure the angle with respect to the surface. And it's kind of logical, it kind of makes sense. That's not the way angles are measured in physics, in optics. They're measured with respect to the normal. And normal, remember, in physics, in the force unit, was like a force perpendicular to a surface. Well, a normal is an imaginary line that comes directly perpendicular out of the surface, the smooth surface. You measure your angles with respect to that line. So this, if you took out a protractor, might be 60 degrees. The reflected ray to the normal makes an angle such that theta incident is theta reflected. So the easiest equation in our course, one thing equals another. The simplest equation you could possibly have. Even though it's simple, it is on the reference table. So there it is in our wave section. Theta incident is theta equals theta reflected. So you could always look it up if you don't remember. Now, if you measured this angle and you said, this is 30 degrees, I'm going to make this 30 degrees here, you would get the same ray instead of doing 60 and 60. So you'd get the same answer. So with reflection, it doesn't matter, unless you're taking a test and you have to report that angle. But in terms of as a practical matter, it doesn't matter which way you measure where you measure the angle, surface to ray or normal to ray. But later in the thing we're going to learn, refraction, if you measure the angle here and plug that angle into the formula, you're going to get the wrong answer in the wrong ray. So you just should always be consistent, measure to the normal, always. All right, so law of reflection. Now, this explains why, if I take this laser pointer like this and I aim it toward the back of the classroom, you can't see it because, again, as I said, it goes through the air and it doesn't create any evidence of it, just passes through the air invisible. But if I take a mirror like this and I direct it the right way, I can get it through the law of reflection and hit the mirror. Hopefully the camera is showing that red dot on the chalkboard right here, because what's happening is the light ray is coming in and bouncing off the mirror according to the law of reflection, and then that's why it now ends up on the chalkboard. But here's an interesting thing. If I aim this laser like this, so you see that angle, and I go like that, you can see that dot. Hopefully the camera can pick it up. That means that the light hitting this chalkboard is not following the law of reflection. Because if it followed the law of reflection, it would come in, hit like this, and then bounce off. Well, maybe I'll do the couple meter sticks. It comes in like this, and then it should bounce off like this and head over and hit the wall over there. And none of the light should go to the camera if this law of reflection really held. But what instead happens is the light comes in like this, and then it bounces out toward the camera like this. And if I go like this, like if this were the surface, the light's coming in like this, and then it's going to the camera like this. These angles are not the same. So what's going on? Why is the law of reflection not holding when I, oops, that's the purple one, doesn't show up that well, green, when I aim at the board like this? And the reason why is because the chalkboard is not a smooth surface. You might be saying, I don't know, I come here, I don't feel any bumps. It feels pretty smooth to me. Well, your finger is very big compared to light waves. Remember, a light wave is less than a millionth of a meter. So when that tiny light wave hits this surface, to the tiny light wave, all the imperfections of the surface that you can't feel are apparent to the light wave. In other words, this is not smooth on a submicroscopic level. In other words, the scale of the light. It is a rough surface. It might even look like a mountain range to the light. And so what happens when you hit a rough surface is something else called diffuse reflection. What I've done here is I've kind of modeled a rough surface like this, a jagged, peaks and valleys and stuff. And look at all these red lines, these incident rays. They're coming in all parallel. But look at this one. It hits right here. And it reflects according to the law of reflection and ends up careening out this way. This light ray comes in and reflects off that surface off in this direction. This one reflects up this way. This one kind of ricochets that way. And if you look at all the reflected rays, they go every which way. So when light comes in and hits a rough surface, it gets scattered in all directions. In fact, most of reflection that happens in a given room is diffuse reflection. When the light fixtures emit light and hit my sweater, it scatters the light every which way. So if someone sitting over there could see my sweater, someone over there could see my sweater, because the light goes every which way off of my rough sweater. So tabletop, paper, notebook, jacket, shoes, all of it's diffuse reflection because none of it is very polished, smooth for the light, on the scale of the light. So I'll create a pause so you could copy these notes down. All right, another thing about reflection is that, as you know, every morning you probably find this out, it can create images. You get up in the morning, you want to see, how's your hair look so you could fix it before you go to school. And you could see a reflection of yourself. So how does that happen? How is it that we can see reflections of things? That's the topic of the rest of this video. How can we understand this, use this law of reflection to understand what's happening when you see images in a mirror? So first what I'm going to do is I'm going to show you an image in a mirror, and then I'm going to show you how you could use the law of reflection to figure out what is going on. All right, so let me reconfigure the camera. How much would you pay for a magical device that instantly doubles the amount of money that you have? I have such a device. to prove it, to show you, I'm going to take this penny and instantly make it 2 pennies. So, ready? 2 pennies. See that? One right there, one right there. And to show you and prove that it works with any amount of money, let's try it with a $20 bill. $20, $40, right? Well, obviously it's just a mirror, and you're intelligent beings, so you understand that it's just a mirror, nothing magical. But to animals that have a simpler brain, that's quite a leap. I've heard that if you put a mirror in front of a Japanese fighting fish, it starts posturing to start fighting because it thinks that that image in there is another fish. Or birds sing to their reflection. So very few animals understand that a mirror is just producing a replica. But how does that happen? So that's what we're going to learn about next. How does this coin here produce an exact replica inside, like there's another coin there? The answer is through the law of reflection. So we're going to do what we call ray tracing to see exactly understand how that second image is produced. So let me reconfigure the camera. Now, before you can understand how that image of the coin was created in the mirror, you have to be able to first understand a couple things. One, how can I tell where the coin is with my vision? Well, I look at it, right? But how do my eyes and how does my brain detect where this coin is? A clue can come from when I take this coin from far away and I bring it close to my eyes. Usually, when I do this in class, students start laughing. You're probably seeing my eyes crossed, and then when I bring it far away, my eyes become uncrossed. When I bring it close, my eyes are crossed, and far away, they're uncrossed. And the reason why is each eyeball, my eyes come crossed, is each eyeball has to turn in when the coin is close, and that tells one of the ways my brain can tell that the coin is close by my eyes coming in, and that the far away is that my eyes are spread out. So that's a big piece of the picture that will help us understand how that image is created. So I'm going to do the rest of this video on this board here because what we're going to be doing is drawing reflected rays, and in this application, accuracy is critical. So the chalkboard doesn't lend itself to accuracy because of the nature of the chalk. So the paper and pencil will be better for our purposes. So another thing I want to point out is that in the Google Stream, I included a document that has a bunch of protractors in it. What I want you to do is to cut out all these protractors very carefully, very precisely. And the reason why we need this, a couple reasons. One, if we were in class, I'd hand you a protractor like this, but many of you are not in class, so you won't get a protractor. Another reason is that this protractor is actually not that convenient. Very often it's too big. Like what if you were measuring the angle of a little tiny triangle here? Well, this is way too big, it wouldn't give you an accurate answer. And another reason why is that the numbers here are misleading in optics. For example, if you put this on the surface like this of a mirror, this is the normal, which is not 90 degrees as labeled on the protractor, it's actually 0 degrees. So none of these numbers are helpful in optics problems. In all these protractors, what I did is I removed the numbers to prevent you from getting misled by those numbers. All right, so we're going to, again, the goal, figure out why we saw that image of the coin. But first, what we're going to do is we're just going to practice how to construct a reflected ray. So what I want you to do is to draw the mirror, a mirror here, and make it maybe big enough space so you could use maybe like your middle-sized protractor. Could I see that on the screen? Maybe I'll have to use the biggest one so you could see it clearly on the screen. All right, yeah, that's better. So that, you know, this fits in the space in your notes. And label this the mirror. And what I want you to do is just make a ray come down and hit the middle of that mirror. And it doesn't matter what angle you pick. Just make it randomly come down and hit the mirror like this, and I'm going to label this the incident ray. Again, Regents likes these little labels. So what I'm going to do is now, at this point of impact, draw a real careful arrow so I don't blurry things up. I'm going to put my protractor so that this corresponds to the point of impact, and the bottom of the protractor aligns with the mirror as precisely as I can. And I'm going to put a little mark over here so that I could construct a normal. And what I'll do is now make a dotted line, and maybe I'll just label that normal. So go ahead and make a random incident ray, and at that point of impact, a very precise, accurate normal 90 degrees to the mirror. Go ahead and do that now. Okay, now it's time to construct the reflected ray. I'm going to bring my protractor back here, put it in the same alignment as before, and I'm now going to measure that incident ray, not to the surface, but to the normal. So again, the numbers are gone. I'm just going to count over from here. How far is this line from that line? The circles represent 10 degrees, so I got 10, 20, 30, and I'm a little off to the side because the camera's in the way, but I see about 31.5. So I will say theta incident here. Theta incident equals 31.5 degrees. Now yours is going to be different because you picked a random ray. So it might be 41.7 or something like that. But whatever it is, measure it accurately to the best of your ability. Go ahead and measure your incident ray now. All right, now I have to construct a reflected ray. Maybe I should have just left the protractor there, because I'm going to take this line with the normal, and I'm going to go 31.5 degrees the other way. 10, 20, 30, 1.5. I'll put a little mark right here. There. And now I will use my ruler to construct that ray. And I'll label that reflected ray. Again, Regents likes these labels. And now maybe I'll do something like this, which equals to. So go ahead and make your reflected ray, whatever your angle was, make the same one. Go ahead and do that now. All right, so you have to be able to do this. This could come up on the Regents, and you would be graded. The teachers would come as they're grading this and see if you're more than like a degree or two off, you lose credit. You have to be able to draw these extremely accurately to get credit on the Regents. All right, now back to that coin. So let's make a new section here. Again, I'm kind of off to the side because of the tripod, the camera. All right, so what I'm going to do is I'm going to put a coin over here. And what I want to do is leave enough space for whatever protractor you use. Put the mirror at least as far away as the protractor. So maybe I'll put the mirror, actually, you know what? I'm going to have to use a smaller one. Yeah, because you want at least as much space below over here as above. So I'm going to put the mirror right in the center of my space. I'm going to need that space. And I'll just draw as horizontal, best I can, a nice crisp horizontal line with a ruler. And maybe I'll put the mirror label here. As we saw, we had an exact replica of a penny somewhere behind the mirror here, looked just like a penny. How do we figure that out? What I'm going to do is imagine two light rays coming from that penny. Really, they're infinite light rays, but we don't want to get carried away here. We'll just draw two. Here's one. Just pick it randomly, kind of like going more into the mirror, not straight down, but you know, a little steeper. And then pick another line like this. That's maybe, you know, like 45 degrees or something. Two light rays coming off that penny. These are two incident rays. What I'm going to do is do this for both of them. So right here, I'll put the protractor for this ray 1. And there is the mark for the normal. And I'll go ahead and make the mark for the reflected while the protractor is here. So I got to measure the incident angle of this ray right here. 10, 20, 1, 2, 22 and a half I'm getting. So I'm going to go 10, 22 and a half. All right, so there. Now I'm going to go ahead and draw in that normal and draw the reflected ray. Oops, I'm a little off. I missed the mark by a little bit. Again, this is the path of ray 1 upon reflection. So go ahead and make your reflected ray now to the best of your ability. Again, be as accurate as you can. I said 22.5, whatever that angle was. Yours will be different. It might be 19 or whatever. We'll make it 19, whatever it was. Go ahead and make your reflected ray number 1. All right, now I'm going to do that for ray 2 as well. So I'm going to put my protractor here at the point of impact, line it up with the mirror as best as I can, and then what I'm going to do is I'm going to put my dot here for the normal, and then I'm going to count the angle between the normal and ray number 2. So I'm going to go 10, 20, 30, 40, 45, looks like 45.5 for me. 10, 20, 30, 45.5 would be right around here. All right, so let me construct these rays. The normal first, and the reflected ray going off like this. Let's see if I could do a little bit better on this one. Yeah, better. And let's label that 2. So go ahead, make the second reflected ray to the best of your ability. Again, it might not be 45 degrees, it might be 50 or whatever it is. Make it accurate on this side compared to the original. So go ahead and do that now. All right, now, these 2 light rays bounce off the mirror, and what do? They go into my eyes. And remember, when I did that thing, that funny thing with my eyes crossing, well, maybe this eye would be around here. Okay, so the funny thing with my eyes crossing, that told me where the penny was. Wherever my eyes, we say, converge, they kind of cross-eye into a point. Wherever these light rays cross as a point is where my brain detects the image of the coin. So what we do is we extend these lines, because again, our brain doesn't perceive the reflection, it just perceives these lines coming from the coin. And I'll extend this, but it's important to remember that you're extending the reflected lines, not the incident lines, the ones that reflect with dotted lines. And they intersect. Oh, I'll put another couple dots here. All right, so see this point of intersection? That's the true path of the light rays. They bounced off the mirror and went to my eyes, but my eyes are crossed at this point right here. So my brain perceives an image here, and this is the original coin over here. And that's how it comes to pass that your brain sees 2 coins when there's only one because of the presence of the mirror and the reflection. So go ahead, make sure your diagram is complete now. All right, so that's it for today, but I want to just recap. Remember, I talked about what light was as a wave of a very short wavelength and how that allowed us to create these collimated beams or light rays, which helped us analyze and understand what happens when light reflects. We learned the law of reflection, theta incident equals theta reflected with respect to the normal, and we also learned how to construct accurately reflected rays, which is part of the Regents. Yes, you have to be able to do that with a protractor and be accurate to within a degree or 2. So practice, practice, practice. And then I mentioned image location, Why is it that we see exact replicas of objects in a mirror? It's because the rays reflect off the mirror and then spread out and diverge. And when those go into our eyes, our brain traces those back into space and perceives an object where those lines cross. That was the ray tracing that we just did. So now the homework, there's 1 page, the 2 pages of worksheet. 1 page, you are just taking those 4 rays and drawing them to the mirror and drawing them accurately to reflect. So you're making 4 constructed rays, continue those incident rays till they hit the mirror, and then make them reflect at the right angle, at the proper angle, and then also write what the incident and reflected angles are underneath that image. The second page you'll see will be 2 practice problems where you're doing ray tracing with those coins. And so what you're doing is you're taking the lines I already started for you, continue drawing them till they strike the mirror, and take those 2 lines and reflect them accurately, then trace them behind the mirror. Where they cross is where your brain will perceive an image of a coin. So that's it. I hope you enjoyed the physics. I hope you enjoyed the beautiful demonstrations I had earlier with the light and the lasers and the smoke. I had fun. I hope you had fun. And I'll see you in the next physics video.